Okay, let's get started. Okay, good morning, everyone. Let's get started. So, I'd like to welcome everyone to ANRW 18, which is not the first ANRW, but it's the first time we've run it the way that we've run it this year. So I'm really extremely personally excited to be in the room with like amazing academics and amazing IETF folks. The whole reason we did this was to get everybody together. So I'm extremely excited just to look around the room and see who's here. For academics, if this is your first time at IETF, you're sitting with some of the people who make decisions about the protocols that we study in the lab. So this is your chance to talk to them, get their feedback, work with them, and so on. For the IETFers, you're sitting in the room with the researchers who do some of the leading work on network protocol, measurement, and design. And so this is your chance to actually work with them and convince them to get their stuff into the standards. So I'm extremely happy and excited to see everyone here on behalf of myself and my co-chair, Dave Chofness, who couldn't make it, unfortunately. Okay, so I just wanted to go over what our goals were when we rebooted this conference this year. Our goal is around academic research in wide area networking and wide area security. So in particular with a focus on the core internet and also with a bit of interest in cryptography, sort of mirroring the topics that are focused on here at the IETF. Ultimately, what we'd like to achieve by bringing this group together year after year, which is what we hope to do, is to transition more research results to practice. And so I wanted to spend like a few minutes this morning. I've come to several IETFs. I think this may be my 5th or my 6th one. I'm not sure. And it's really hard to understand exactly what goes on here if you show up for the first time. So I would take the liberty of just trying to expose academics to what I've learned after 5 years of coming here. And so really, one thing that we as academics know how to do is to disseminate our results. We know how to write papers and give talks and present them. And so here's your chance to give your talk and present it in front of the people who design the core internet, and that's great. So that's the first thing. The second thing I really want to encourage people to do is to just not view this so much as a black box. I remember myself, when I first started coming, I thought if I would like tell people enough about what I was working on, it would somehow magically like get into standards and stuff. And some of it sort of a little bit did, but it's not that easy. And so this is a chance. So this is your chance to actually connect with the people who know how to work through these processes. And so if you're someone who's interested in TLS, DNS, BGP, NTP, RPKI, certificate transparency, we have all the people who work on that. I think most of them are actually right inside this room right now. You can talk to them and tell them what you're working on and try to get them to work with you. And the other goal that we wanted to do, we wanted to make this place a home for longer term networking research. So some conferences are really focused on novelty. This conference is not focused on novelty. This conference is focused on presenting your results and seeing how do you make them practical. So if that means, you have to write the second or third paper on a topic because the first one you wrote was completely wrong and completely impractical, we want this conference to be a home for that kind of work. And that's important because if you look at how things work in the IETF, there's iteration over iteration over iteration over iteration. And so we wanted to make that a home for that kind of research. So this is my, to academics, please don't just hope that others will standardize your work, try to get involved in the process. So just a little bit about the stats for the conference. Here's the program committee. Thank you everyone for your hard work. The steering committee did a lot of work other than just steering, including organizing all of this. So thank you everyone who's on this list. Especially Matt, who responds to my emails within half an hour and does everything I ask, so thank you. We had 44 papers submitted. We selected 11 talks. We accepted 18 posters as well. So there's going to be 2 poster sessions. It's all the same posters. They're in that room over there, so you have access to them during lunch, and then after the last talk session, we'll have the poster room open as well. So hopefully we'll have continuous discussion on posters. And then to kick off the process and to sort of make the conference interesting for the world, we also invited 5 talks. So some of the talks are invited. The process that we used for that was the PC nominated papers, and then the PC selected the speakers. So these invited talks were invited collectively by the PC altogether. So those are the stats. Okay, this is my, like, I know that there are people who have been doing this for a long time, so probably what I'm saying is not exactly right, but this is my view of how the IETF standards process works. And for sort of, I wanted to spend like 2 minutes just telling you a little bit about how you can potentially work through this process if that's something you want to do. So IETF has this thing called internet drafts. These are not RFCs, these are documents that you write. Anyone can write one. You can write one right now and submit it. There is no requirement that you be an IETF or even go to an IETF. You just write one and you submit it. That's it. Okay, so that's an internet draft. The thing is that this thing doesn't necessarily carry too much weight until you do a lot of other things, which allow you to get your internet draft adopted by a working group. Okay, so the IETF is divided into working groups. There's lots of different things that people work on. So DNS has a working group, TLS has a working group, BGP, and so on. So what you want to do is if you want to submit your internet draft and get it somehow adopted by the working group, then it becomes working group business and it can walk down the road to becoming a standard. Okay, so how do you get from here to here? So you have to figure out what working group you're going to actually submit it to. That may not be completely obvious. So for instance, with our draft here, we found a home in the CFRG, the Crypto Forum Research Group, but we actually started in the Security Area SAG group. I forget the acronym. So we didn't know exactly where this draft should go. Find a home, post your draft, post to the mailing list. Hopefully you'll be given a slot to present to the working group, and then you'll get a lot of feedback from the working group. This will go on for a while, and if you're lucky, your draft will be adopted. So once your draft be adopted, it's part of the working group's business, and you can start to push it forward to becoming a standard, after which you do more iteration, okay? Now, once it's an adopted internet draft, it's still not an RFC. It has to go down continue down the road. The authors typically revise the draft with feedback from the working group, and you revise it, you present it to the working group, you revise it, you present it to the working group, and eventually you get to something called working group last call. And if you get to that and you get past that, then you're really on the road to becoming an RFC. I don't really understand what happens at this point because I've never done it, but this is, if you're here, you're winning, okay? So how do you, so what I really want to say is, like, as an academic, if you want to drop a draft, just go write it. It's fine. You can do it. Nobody can prevent you from doing that. The issue is just getting your draft adopted and finding a home for it. So what I wanted to spend like 5 minutes on was just how you might do that. And just so you see, like, iteration, right? So this is a draft that started out by Fujiwara. At the top, you can see its 0th version. It went through 3 iterations, okay? And then it was adopted by the working group on June 2016. It went through all these iterations, 10 iterations, and then it became an RFC, RFC 8198, right? So that's the process that you might have to go to. You might have to be a draft that you've revised yourself before adoption, and then it gets adopted, then you revise it with input from the working group, and then it becomes an RFC. So this is the process you go to. It's pretty long, but that's how it works. Okay, so my last point, how do you actually get through this process? So this is my personal trick. My first rule, find at least one IETF native who will help you through this process. So make this person your co-author on the draft. You can write the draft yourself, but they can become your co-author. And why is this good? First of all, they'll tell you how to write the draft. They'll help you how to write the draft. They can help you get a presentation in front of a working group and even figure out what that working group should be. The presentation in front of a working group, to be honest, for the academics in the room is just like an academic presentation. There's nothing like particularly unusual there. But then it starts to get different. You have to post to the mailing list, keep up with the responses to the mailing lists, revise your draft in response to the mailing lists. And then you kind of go through a process which is basically kind of getting to the consensus that your draft will be adopted by the working group. And this is where the IETF native is key. Getting through that process is complicated because there's a lot of views in the room. You have no idea who these people are if it's your first IETF. So if you actually have someone who understands the different viewpoints about the protocol and what's going on in the working group, you can get through that process. Also, the other thing is there's 3 IETFs a year. Most academics cannot go to 3 IETFs a year. So if you have this, this co-author, they can go. And they can keep you in the process and make sure the working group is paying attention. And also really, really helpful for getting your code deployed in open source projects and things like that. So these are the connections that you need. My second secret is you can have up to 5 co-authors on your draft. So as an academic, do not put all your academic co-authors on your draft. As authors, you've filled up 5 slots and you have not used them on IETFers. Don't do that because you won't have the people behind you to help your draft get through the process. So sometimes I've done one where it's just like me and one other co-author on a paper that had 6 people. We put them in contributors and we add co-authors as we go that they're helping us through the process. Okay, last thing, drafts need to be watered and fed. They expire after 6 months. Don't let them. Just, change something and make it not expire. There's also a deadline 2 weeks before the IETF. Don't miss the deadline. And then another really important thing is like being here and talking to people is really the way you get consensus around your draft. So it's not just coming in and listening. Make sure you're talking to people. Try to get introductions to the people who are influential in the working group that you want to influence, and get them to pay attention to your draft. And that's a way to kind of push things forward. So that's my advice. Thank you for listening. And the last thing I wanted to say, second last thing I wanted to say was, let's build a little bit of buzz around this thing so it's huge next year. That's our hashtag for Twitter if you'd like to use it. And let's thank the sponsors as well for having us all here. Thank you.
Okay, thanks, Sharon. That was great. I'm Nick Sullivan. I'm chairing the TLS section of this conference. TLS is Transport Layer Security. It's one of the main protocols that the IETF worries about on the security front. So we're going to have 4 great talks about TLS, and the first of which is being set up right now. And let's see, you have everything you need. Yeah, I'm very excited for this group of talks. I think there's a lot to learn about studying TLS in the wild, there's a lot to learn about how TLS has been deployed. It's been an exciting couple years for TLS in terms of deployment. HTTPS adoption has grown significantly, and we're on the verge of the publication of the latest version of TLS, TLS 1.3. So without further ado, I would like to welcome Kieran Shitlev from the Technical University of Munich. Thanks, Kieran.
Thank you, Nick. Hello, everyone. I'm a PhD candidate at Technical University of Munich. It's my first IETF, first ANRW. I'm really happy to be here. And I'll tell you a bit about the measuring adoption of security additions to the HTTPS ecosystem. So it's a bit of a broad range of additions that we've measured over the past year. This talk will basically cover 2 papers in 15 minutes, so I'll talk real quick and also give you quite a high-level thing. So if you really want the details, these are the 2 papers. The first one was with Johanna, who is also here, Oliver, Lexi, Georg, and Ralph. And the second was with TJ, Jens, Oliver, Johannes, Roland, Ralph, Dave, and Alan and Georg as well. The first one, sorry. So in the first one, we said IETF is really bringing a lot of additions to the HTTPS ecosystem over the years. And we said we want to set out to measure the quality and quantity. So how many people do use it, and do they use it in the right way, or do they have typos, wrong copy-paste from tutorials when using these security additions? So what we did is we did a large-scale scanning campaign. So almost 200 million domains, 2 vantage points, IPv4, IPv6. It's really good if you use a large target population to get a good sample from the internet and not, for example, a top list, but that's a different topic. We also did passive observations from 3 continents to also mirror the view that people really use of the internet, not just a long list of domains that maybe are not in use. So straight to the results, we measure all these domains and we measure a lot of things per domain. And what we looked at is the first thing, when were those things standardized? Typically in the recent years. How big is deployment? So 100% would be about 55 million. So you can see some were really quite well deployed. And then what we said is we think that deployment is correlated to effort for the administrator to set something up. We had some metric for effort, which also involved Do they have to make decisions? Do they simply have to say on off, or do they actually need to think about it and configure something? And then risk to their website. Because, for example, if you use HPKP and you insert the wrong key, your website is not available anymore. So that's a high availability risk if you get it wrong. And we find there's pretty much a correlation to these things. So SCSV, for example, which is a downgrade protection pseudo-cipher suite, has the highest deployment, and that's because it simply comes through an OpenSSL, or whatever your SSL library is, update. So most site admins probably don't even know they're using this. It just comes by default. So it can quickly gain big deployment, while other methods can have a really hard time winning a user base. And that's pretty much the high-level takeaway. The full paper has a lot of details per thing that we have measured, what typically goes wrong, which sites adopt it, also if it's more adopted by top sites or sites outside the top 1000. And what also, as you see, HPKP is high, and also Chrome. Around IMC last year, when we published this first, Chrome also announced that they will remove HPKP because it's just too dangerous for people to get it wrong. Then we did a follow-up paper where we looked deeper into CAA. CAA is, it's been standardized in 2013, but it just became effective last September. And it's a DNS extension where a site owner can enter, looks like this, where a site owner can enter, perfect, which CA is permitted to issue certificates for your domain. So as a site owner, you can control which CAs you trust to correctly issue certificates for your domain. And this, per CAB forum vote, became mandatory in last September. So we said, let's take a deep look into this. Let's see how this new standard gets started in the internet. What are the things that go wrong? What are the things that go good? And let's see how we can learn from that. And we did that using 3 angles. The first is a controlled experiment, where we said we set up some test domains, buy certificates, and see which checks do the CAs really do, and are they in line with the standard. Then we also said we want to see the market adoption. We want to know how many domains do actually use this new extension, or is it just something that got introduced and no one is using it? And the third one, if you're adding something to the DNS, you must be aware that a large portion of the DNS space is not managed by people themselves, but people host their DNS on whatever web hosting platform. And if these don't support your DNS extension, it will not gain a big market share. So we also bought some domains with the big hosters and had a look how many do support setting and configuring CAA. So for the first one, we set up 6 test domains, and basically we don't have to get into the details, but you can imagine there's a number of dimensions where you can do things differently, and we set up those 6. For example, the first one is correctly DNSSEC signed, and it simply says no CA must issue any certificate. So that's a very basic test that any CA should get right. The second one, for example, is DNSSEC signed, but it times out. Our server will not respond to your query. So in that case, you're also not permitted to issue. And there's some more of these. Some are informational. That's where the standard is ambiguous. So CAs can or cannot issue depending on how they want to go about it. We added these mainly so we get some more insight into how are decisions taken at these corner cases. So we set up these 6 test domains, and then we did 2 rounds of testing, 1 month apart, where we bought certificates from, I think, 12 CAs. And after each round, we did we basically told the CAs which cases went wrong, which ones went good. And typically they were very happy about the free testing and fixed things. And if we look at the results, this is basically it. So a red I means issued but should not have issued. The columns are the test domains and the rows are the CAs. And I think there's 2 quite interesting takeaways from this. First, whatever column, you'll find a red I. It doesn't matter which case you're testing, some CA will give you a certificate, although they should not. And the nice thing as an attacker is you can test an almost infinite number of CAs. So from an attacker perspective, this is clearly not good. No matter how a domain is set up, you'll find some CA that will not adhere to that specific portion of the standard. You can also see some columns have quite a lot of red. For example, timeouts on DNSSEC signed domains are apparently not that simple to recognize if you use standard libraries. So a lot of CAs had their issues with that. You can also see, but this is not that much a name and shame game, that some rows are really green and some rows are really red. So there's also some different levels of rigor that CAs displayed. Good. Then for adoption, we basically did that large-scale scan from earlier. So we have this list of, by now it's I think 200 million domains, and we just scan them all and see which ones have CAA records and what is their configuration. And what we did, and which is a really nice thing, is these scans run 2 times a day, and these scans automatically get post-processed and put on a website. So this is the website. And basically this gets rewritten 2 times a day. So until that server dies or whatever, this will continue running and update the status of CAA. And I think you can also see from last March when we had 3,000 domains to now, there was a big jump yesterday, 200,000. You can see that there's a clear uptick in adoption in the market. You can also look at all the nitty-gritties and details, like how many use issue, how many use issue wild. And also one thing that's really interesting is name server inconsistencies. I think no one is surprised that name servers are inconsistent in the internet, but in this case, there really shouldn't be. It's a security feature, right? It shouldn't depend on which of your authoritative name servers I'm asking if I'm permitted to issue a certificate or not. So, and it keeps existing. So there's always around 2,000 name servers or 2,000 domains with name servers that have inconsistent answers to CAA queries. We did some deep dives, and frequently it was something like some name server used a version that, so they would use different software versions, and some didn't support the record yet, for example. But that would also mean that the trend should be decreasing. So I don't think that's the key element to this, but it's really hard to find out what's wrong with these name servers. You can also see these anomalies. That's typically some hoster changing something and affecting a lot of domains at once. Good. And then also for DNS provider support. So basically we identified the 31 biggest DNS providers in the comnet.org zone files. And these biggest 31 make out 54% of all domains. And for those, we bought domains and did check, can we configure CAA records for these DNS operators? And it's looking somewhat good. So the biggest one actually supports CAA. You can configure it, and that's about, of these 50%, another 50% that actually support CAA. But there's also quite a long tail of hosters that do not support it yet. And also, for example, one of the hosters had it wrong in the beginning. So they would set the wrong bits in the flex field, for example. But that hopefully got fixed. Good. So if we quickly summarize, HTTPS security extensions differ vastly in scope and deployment, and also the quality of deployment is quite different. Especially in HPKP, we found quite some domains that had simply copied tutorials from the internet and put in the key from the tutorial, which is really bad. So there's a bunch of these details in the paper where we really look, how do people set it up? And typically if you Google the key and you find some tutorial, you know, this didn't go well. And what also stands out, these low risk and effort technologies are widely deployed. So really, if you standardize something, make it as simple as possible, because people maybe won't have time or won't be interested. They will just copy paste something and hope it works. For CAA, we did a deep dive, and we really found that mixed rigor, let's call it. On the CA side, we see that market adoption is picking up, and that also DNS provider support is a real critical factor if you want to change something in DNS that users are supposed to use. And also we make the data, software, and tools available, and also for CAA, the live website that is running, and also other data in detail is available. Good, thank you, and I look forward to questions.
Thanks. We have 5 minutes for questions. Please come up, ask your questions.
Hi there, I'm Daniel Kahn-Gilmore from the ACLU. Thank you for this work, this is great. In your guidance for what to do when you're proposing a standard, you recommend making it as simple as possible. Some of the tools that we're deploying here are actually complex sort of in their nature, right? And so I wonder, what you've done here is you've given an example of making a tool that demonstrates whether something is working correctly or not. And I wonder whether you see this kind of work as something you can do to promote adoption of the standard, right? So it's not just about is the standard as simple as possible, it's about what tool is available. So I mean, if someone's writing a standard, what step would you recommend that they take in terms of building a testing tool or providing default configurations, or like you can make something that's complex simple by making choices for people, right? So I want to encourage that, like this kind of work as part of getting a simple to work. So I hope we see more work like this. You're helping me with that.
Thank you. Yeah, and I fully agree. For CAA, there's a great generator tool on the web where you can really just tick boxes and it will put you out a copy-paste config for your site. So I think these tools really help, and I don't think they're that hard to set up to put as an addition to an RFC or something.
So I have a question. A lot of this measurement happened a while ago. What changes have you seen in the internet for the deployment of, say, that first chart where you had CT and a bunch of other things?
So
how have things changed since the measurement?
So these measurements were April 2017. We keep running them, but we haven't evaluated all of them again. I know that HSTS is really rising. I had a look last week or so, it was by 9 million or something now. So HSTS seems to be quite well deployed. CT, of course, has seen strong adoption. CAA has gone up from 3,000 to 200,000 or something. I've not checked TLSA or HPKP recently. I would assume they're both still dormant.
So in measuring this over time, what events or what different actions by either service providers or browsers had the biggest impact on improving adoption for any one of these? Do you have any anecdotal evidence that corresponds with any of these jumps?
Yeah, so for CAA, it's clearly hosters enabling this for default for all the customers. For CT, we haven't done a chart over time yet, but I would assume that CT has significantly gone up, mostly driven by the Chrome enforcement. So I think browsers have a lot of market power here to push things, and I guess something like SCSV that comes through library updates will also be mainly driven through that.
Any other questions? Okay, well, let's thank the speaker again. And the next talk is going to be again by Kieran. So the first was an invited talk, and this is another presentation of a talk that was submitted, and this one had many more co-authors as well. So I'll give it back to Kieran.
Thank you. Sorry for having to endure me again, but I promise this one's also really interesting. This was joint work with Matthias and Georg. We published this at TMA last year, and it describes one of the ways how TLS can really go wrong in the wild, like really bad. What you probably all know, and this has been known for a long time, and some reviewers were also friendly to point out that this is not new, but apparently everyone knows that TLS 1.2 handshake does not encrypt certificates, which is maybe not that much of a problem on the server side, but definitely on the client side. So client certificates, if you look at them, the stuff that is in there is just incredible. So it's used by VPNs. It often has your clear name in it. It's used by governments for voting things. It definitely has names, company names, a lot of private data in it. And this is sent unencrypted in TLS 1.2. Thankfully, it's fixed in TLS 1.3, but I guess it will take some time until TLS 1.3 is actually the majority of handshakes. Back when we discovered this, TLS 1.3 was not standardized yet, so just as a context. So where is TLS client certificate authentication being used? It's used in network authentication. It's used a lot by VPNs. OpenVPN is using it. Edge Connect is using it. HTTPS is using it. Also some IoT protocol, MQTT, was at least planning to use it. Also all these remote device management solutions like Mobile Iron and whatnot, they are also using CCA. And to our surprise, also Apple push notification service has been using CCA. And Apple has a lot of deployed devices. So it was 1 billion in 2016. It's probably more by now. And it also has a lot of iTunes on Windows running. It's another 800 million or so. So there's a huge user base. And just as a brief recap, what are push notification services? Basically, they exist to save energy. So instead of all your apps pulling data from all these servers, you have this one channel in the backend where just Apple is telling your phone, hey, WhatsApp has a new message. They basically exist on all the ecosystems out there, and they're typically tightly integrated, so it's not possible to disable them. And they're also always connected. Apple push notification service, every time you connect to a Wi-Fi, it will connect. On mobile phone, it will remain connected over long times, but if you're just on Wi-Fi, you will have continuous connections every time you join a new Wi-Fi. So there's a lot of logins to be observed. And what we found them to be using is that they used client certificates for login to this push notification service. So every time you connect to a Wi-Fi and don't have cellular internet, it sends the certificate. The certificate is generated at device setup, so with a second precision timestamp. So I can actually tell when did I set up this phone the first time. And there's very unique cryptographic material in there, like serial number, that setup time, which is pretty unique. So you can clearly identify a device if you see it several times. Now, we looked at, can this be used to track users? Obviously, it can only track devices, but if you can track my iPhone, you can pretty much track me. And we looked at 2 out of 4 attacker types that you could come up with. So if you're Apple, you have better means to track your users. Also, if you run this Wi-Fi, you have better means to track your users. The interesting attackers are regional attackers that have access to large networks, like a university campus, a city network, or global adversaries that potentially can access several core networks. What we did is, for the regional adversary, we looked at the scientific network in Munich and said, can we track users in this network, which has about 100,000 users. So it's a fairly big regional network. And for the global adversary, we looked at routing of these logins, through which core networks are they being routed. Good, so we did some passive capturing, 2 weeks of traffic using where we captured these logins. And this is private data, so we followed a lot of regulation by our IRB and also by us, so that we would not attempt to identify users. We will not publish the identifiable data. The measurement machine is actually not on the internet, so lot of precaution so that this doesn't go wrong. And what we found, basically, if you look at the issuer distinguished names, the vast majority of certificates is Apple. And then there's, for example, these VPN clients, AnyDisk, apparently some Ricoh printer scanner, whatever thing is also using client certificates. So it's clearly Apple, the majority of certificates observed in client certification handshakes. And the next thing we did is I looked at actually this laptop and got the certificate for this laptop and then tracked that certificate over 2 weeks. And you can see pretty well when I go to work, if I work from home, if I work from VPN, if I sit at my desk, if I have meetings all day and go from room to room. So you can really tell quite well what a person is doing in this network. This is the one exception, of course, because I gave informed consent. Then we looked at what percentage of certificates is traceable. And most certificates we see for 3 or more days. So there's 35% or so that we only see once on one day, but most certificates you see recurringly. So you can really say all those over there, 60% or more, or 40% or more, you can really trace over several days and tell when are people coming to work, where are they working from all these things. You can, from the certificate type, tell if it's iOS or desktop certificate, but I won't get into the detail here. It's just a slightly different curve. Good. And then the next thing we looked into is this global tracking feasible? So from the past slides, I would say clearly if you're a regional attacker, you can do a pretty good job in tracing individual users. What do you do on a global scale? So what we did is we got the backend servers from basically observing all these handshakes. We know pretty well what backend servers these iPhones, macOS, whatever devices talk to. And the majority of APNS logins is going through few central IXPs, ISPs. So the APNS backend is, as you would expect, globally quite well distributed. And we did global measurement campaigns through RIPE Atlas and looked at how many central networks would you have access to trace users globally. And basically, if you get, this is also not surprising, but interesting to see, if you get the top 10 IXPs or ISPs, you can trace 80% of devices. And I think there are attackers out there that might have that capability. So this was also rather shocking to find. Then once we had found all that and discovered the scope of it, we talked to Apple's product security team, which was really a positive surprise. So they were really within 2 days or something, we had a good discussion, several phone calls, and they had several engineers fix this within a couple of weeks, which is, I think, quite impressive given that there's billion devices, lots of backend servers affected. So I was also quite impressed that this was done so quickly and so professionally. And this was then fixed in January 2017 in iOS 10.2.1 and whatever the iTunes on Windows and whatnot devices affected, because this was really, we didn't test it, but this was also for watchOS, tvOS, whatever Apple thing. Basically everything has push notification service in it today. Good, and what's happening now? TLS 1.3 is luckily encrypting certificates now. There are still some things unencrypted that should be. SNI, I'm hearing there's people working on that. And also some application-specific data like the ALPN thing, I think, is also under discussion. For me, that takeaway is really a lot of people told us this is not new. Everyone knows this is unencrypted, it's a privacy leak, it's bad. But still Apple, who is probably employing engineers who know these things, still used it. So I think there was really a lack of awareness of the scope of the problem that you can easily create if you embed traceable identifiers into your protocol handshakes. Especially in this always-on scenario where it's not 1 login per year, but it's 10 logins per day or so happening. So be very careful if you build any traceable identifiers in your protocol, really try to avoid this. Also here we did a fun exercise in terms of reproducibility, which is a challenge in internet measurements. We did this at TMA PhD school, so we ran a half-day lab and gave people the paper and said, in this half day, use RIPE Atlas and try to replicate the results, which was quite a fun exercise, and also it bolsters the confidence in your result, right? If you say 20 people actually came to a similar result. So this is also a fun thing that you can think about, go to PhD schools and offer exercises. You'll get interested people to work on stuff. Good. Thank you for your attention, and I'll take questions happily.
All right, questions at the mic.
So we've actually, I don't know if any NTP people are here in this room, but we've actually talked about this specific issue with the network time protocol and the network time security extensions. And we've done a lot of thinking about how do you avoid making traceable identifiers in NTP, which is essentially an always-on, very low-rate protocol. And so, first of all, this is actually, to me, like, I was like, oh, is this so important, like the unlinkability of sessions, and it doesn't matter. So this, to me, like, really, like, wakes me up a little bit and say, like, yeah, it matters a lot. My actual question is, how do we avoid this with the next protocol? Like, you found that this happened with Apple push notifications, but number one, like TLS 1.2, it's still very, very deployed out there. So how do we like avoid the next giant, privacy leak? And for all the other protocols out there that have linkable identifiers, how do we like keep track? Do we need to, is this just something that we need to always be tracking, these linkable identifiers leaking out in protocols?
I'm afraid I don't know the golden answer to this. I really don't know how to solve this at scale. Maybe it's just a thing where we say, let's hope for a better future and hope that there's not too many protocols that do that as well. We looked at some reasonable close protocols like SSH and found they do that well. But there's so many protocols out there, and I'm sorry, I don't know.
For NTS, this is actually something that we thought about. So for any NTS people in the room, then this is pretty convincing that we should not have linkable identifiers in the protocol.
Any comments with respect to how Apple fixed this? Is that documented somewhere for others to learn?
They never told us how they actually fixed it. They've done away with client certificates. So what you can observe now is there's some ALPN key, but that just says I'm talking the new version of Apple Push, and then there's something in the encrypted payload that we don't know what's happening there.
Yeah. Second question: would you say that there is broad agreement that this is a bad thing? Like within IETF, is it part of the RFC after Snowden, or is there some documents stating that this is not something you should do in a new protocol, or is it just our collective knowledge that that's bad thing? Maybe it's...
I don't know, but I'm sure someone in the room does.
Alyssa Cooper. Yeah, so there is an IAB, so a document which was published by the Internet Architecture Board, which provides some kind of analysis and guidance about linkability in your protocol. Doesn't go so far as to say, like, when designing a new protocol, you must not have linkable identifiers, because at the time, it's actually published, we were just a month after the Snowden disclosures, but at the time it didn't seem feasible to put that requirement on all new protocols, although perhaps that's worth revisiting. And so there is some guidance that's available, but there's nothing strict about actual design decisions. If people are looking for it, RFC 6973.
In fact, there is a a individual draft by Chris Wood about linkable identifiers. That was recently published in June, I believe. Okay, well, with that, thank you very much to the speaker, and we'll have the next person come up. Thank you very much again. Applause.
Thank you.
Where would you like to sit, Kevin? Hang on. Do you want to do it there, or you want to stay here?
I can do here.
Okay. Okay, our next speaker is Kevin Borgota from UC Santa Barbara, who's going to be talking about mitigating the security risks of domain-validated certificates. Here you go. Thank you, Kevin.
Yeah, thank you everybody for coming. Thank you everybody for being here. And yeah, it's a pleasure to talk about some of my past research, specifically this one, which was published at NESS this year, and specifically looking at the security risks that domain-validated certificates, or rather TLS in general, and giving out TLS certificates to everybody might have, and what we can do about that. And the motivation for this is basically looking at what can happen if there's a takeover attack. For example, in this case of Uber, they forgot to actually remove a DNS entry from sao-static.uber.com pointing to EC2, so to Amazon, and somebody figured that out, took it over, registered as, hey, I'm actually sao-static.uber.com, and because of the way that they are setting up single sign-on, it actually allowed everybody who went there to disclose their cookies, and then allowed impersonation attacks on Uber users. And in this case, Arne basically could just order rides wherever he wanted on whoever's Uber account he stole the credentials from. And the reason that this is actually happening is because you have stale DNS records largely. So you might have a domain, for example, cloudstrife.seclab.cs.ucsb.edu, which points to an IP address, in this case, an EC2 IP address, for example, 34.215.255.68. That one's actually still allocated to us, so no need to trying to get that. The question here is, of course, what are you going to do when you actually want to migrate away? When are you going to remove an IP address? How are you going to migrate this gracefully? Are you going to remove this immediately? Are you going to release the IP address once the TTL expires? Are you going to wait longer? So should you wait like 600 seconds if your TTL is set to 600 seconds, or are some name servers going to ignore that and just going to cache it for example, an hour or a day because they figured, 600 seconds doesn't seem long enough. What are you going to do about automatic scaling, for example, if your EC2 instance is set to actually scale up or down depending on CPU loads? Then the IP address might automatically be freed, which might give you a window at which case somebody else might be able to claim that IP address. And if you combine this with, for example, the recent push in the TLS ecosystem and specifically domain-validated certificates, this can actually become a security issue. And just to recap and have everybody on the same page, domain-validated certificates are basically standard TLS certificates. And they're trusted by major browsers and operating systems. For example, Let's Encrypt has been a major player here, and they are credited for one of the rise in HTTPS adoption and TLS adoption in general. And domain validation generally is either pretty cheap or even free. Let's Encrypt is usually free, but Komodo usually charges some amount of money. And most importantly, it doesn't have any identity verification. So it doesn't verify that you're actually the person claiming that you are. It's not extended validation. It's really just who is controlling the domain. And one of the major ways that this is happening today is actually using HTTP-based domain validation. And just looking at HTTP-based domain validation, it works in a pretty simple way. You as a client or a user who is requesting a certificate is actually, you're going to a certificate authority, in this case, an ACMIS CA, and you're saying, hey, I would like to have a certificate for example.com. Then the certificate authority is coming back to you and saying, hey, okay, please host this challenge and show that you actually have ownership, that you can actually control this specific domain that you're claiming you're the owner from. then you as the client or user, you actually say, okay, I'm hosting this specific nouns on my web server, and then you instruct the certificate authority to verify that it's actually there, which the certificate authority is then going to do, and basically step 4. But if you think about this, this actually doesn't prove that you control the actual domain, but what it does, it proves by proxy that you're actually controlling the host behind the domain, right? So you're not actually showing that you can control whatever the domain points to, but you're controlling what the domain currently points to, which might simply be an IP address that somebody might have forgotten to either remove the DNS entry from, that you might have hijacked through, for example, BGP, which there's another paper which basically showed that this is a possibility and actually a problem for domain validation. So that's, of course, theoretically can become a problem. Because an attacker, once they actually are able to do this, they're getting a trusted TLS certificate, which they could use for man-in-the-middle attacks, for example, on a local Wi-Fi, or if they have access to or a large user pool, they could use it for those. There are cases where they might want to use it for malicious remote code loading. For example, Chrome only loads JavaScript nowadays through HTTPS. So if there's still some websites which might actually include something from a domain that was previously simply going to an IP address that was unresponsive, somebody might be able to inject actually malicious code. Similarly, the subdomain attacks that I mentioned in the case of Uber might allow you to steal cookies, which might only be sent through secure only. If it's email, you can exploit the residual trust that might exist in a domain. If you're getting a spam or phishing mail from, for example, saostatic.uber.com, you're probably more inclined to actually believe that some kind of security authority office at Uber or something where you just make up something for the subdomain. The question, of course, then becomes, is this actually a problem? So for the Komodo part, you could get a certificate which would be valid for 3 years. So are there actually a lot of websites where this could be of impact? So what we decided, we look at, okay, let's evaluate whether this is a problem at scale. So we decided to look at, okay, how many active domains point to IP addresses that could actually be taken over, that are free, that anybody who has an EC2 or an AWS account or a Microsoft Azure account or a DigitalOcean account to just try and get an IP address. And specifically, we decided to look at active domains, so domains that are actively being resolved for. Specifically, we looked at the Farsight data set. So we looked at around data from, I think, around 2 months. In total, we looked at 707 million unique domain IP pairs, which we looked at whether a domain might point to an IP address that might not be responsive and that might be taken over, might be possible to take over. And we found that looking at cloud IP addresses in particular, because they're the easiest to churn through, that we found 130 million unique domains that point to cloud IP addresses. And then we also looked at how quickly can you iterate through all of the IP addresses that a specific AWS pool might have. And we did this by allocating one IP address every 2 seconds. And we cycled through around 14 million allocations, and we got around 1.6 million unique IP addresses. And even just allocating one IP address every 2 seconds, you cycle through the entire pool that a specific AWS region has in less than 2 weeks. So, but just going through, you might be able to get a specific IP address in less than 2 weeks. And an attacker, because they don't need to do this only one every 2 seconds, but they can actually do possibly 10,000 requests a second. For them, it's much easier and much quicker. And actually, there are around 700,000 domains for which currently, or rather back in April 2017, for which the AWS IP address was actually free and unresponsive, where somebody could just cycle through the pool, get it, and then claim that they are owning some specific domain that they have no control over beyond the IP address that it pointed to at some point in the past. So what we kind of need to do at this point is that we need to assume that these kind of attacks will happen in the future, and they might even already be happening. We just don't know about it. At the same time, there's no way that we can fix this by requiring some major redeployments or changes to DNS. I mean, just looking at the way DNSSEC has been adopted and how long that has taken, it's not that we can do anything rapidly there. So what we're trying to do is we're trying to some way prevent the abuse a little bit higher up. And specifically, we're focusing on TLS services. And we want to leverage existing standards whenever possible so that we not just trying to make up a new solution that then might take like another 5 to 10 years to actually be adopted. And for HTTP, that's actually, you can take a pretty simple idea. You just use HTTPS with trusted certificates, you use strict transport security, and then you also throw in public key pinning, which basically means, hey, now you've pinned the key, which means you don't really need to do anything. Because when a takeover attack now happens, the attacker actually needs to have the pinned certificate. Otherwise, the browser is just going to say, okay, no, I'm not going to connect to this, which at least reduces some kind of impersonation or takeover attack down to denial of service attacks. The problem here is, of course, this doesn't work for SMTP and other kind of protocols that might rely on TLS certificates. And then, of course, in addition, we have domain validated certificates, and public key pinning is actually deprecated since May of this year since Chrome 67, and now we're at Chrome 68. So that doesn't really work. So we need to do at least a little bit more than that. So we kind of need to work on a better solution. So looking at a better idea is, okay, is there some way that we're just starting for HTTP and HTTPS, we still use trusted certificates, but now rather than issuing certificates at will, we're looking at, hey, is this domain or the IP address behind it possibly taken over? And if so, can we prevent a certificate from being issued in this case? And in this case, this means it also works for SMTP and other protocols which rely on TLS, because if there's no certificate, then the client hopefully is going to say, like, yes, I'm not going to connect to this. The question, of course, is how do we actually prevent certificates from being issued? So how do we identify that this might be a takeover situation where the IP address is not actually being controlled by the previous and legitimate owner? And fortunately, we can here rely on something that the certificate ecosystem has for a while now, and that's specifically certificate transparency logs. And certificate transparency logs, for those of you who don't know, are basically a public append-only log for any kind of certificate that has been issued. The idea here is that you monitor them in case you own a domain, whether there's any certificate that was issued for your domain, so that then you can react. And they're kind of providing you with a real-time-ish audit trail of certificates that have been kind of lively issued. It takes usually a few minutes or up to like 15, 20 minutes until they actually show up. But by themselves, this is actually still problematic. Because this is reactive. The certificate is still being issued, which means the attacker's window of opportunity remains. You as a website owner or domain owner, you actually need to go to the certificate authority and say, hey, please revoke the certificate. This should have not been issued, which is usually a manual process and involves manual validation that you're actually the legitimate owner. So this is going to take a while. On top of that, every single domain owner needs to monitor this by themselves, which the majority of them are not going to do. However, at the same time, we can actually use this for historic lookups. So this one exists, so we can just have a certificate authority basically look up whether a certificate previously existed, which might still be valid, and only issue certificate if this is not the case, for example, or if you can prove that you still have the old certificate, which is exactly what we did with a preventive HTTP-based domain validation. And the way this works is, for a user, it doesn't really change anything. You as a user, you still go to the certificate authority, you request a certificate, but now rather than the certificate authority immediately responding to you and telling you, hey, please post this challenge, they're now getting some background information on the domain that you want the certificate for. And they're basically just looking up, hey, is there any certificate that currently exists that might still be valid, that I should be checking for if it's maybe whoever claims that this person is actually still have. So does client still have a certificate that currently should be, it should exist? And then the certificate authority responds in the same way. Here's the nonce, responds with a challenge. You host the challenge, but this time you're not hosting it on HTTP version of your website or whatever service you're using, but rather you're doing this with the TLS certificate. So you're using HTTPS. And now the little twist comes in that the certificate authority is not only verifying that there's the specific nonce that you have, but they're also verifying the certificate that you're using to actually serve the website. And specifically, it means, hey, if there is an old certificate that's still valid, which whoever is actually claiming to be that website or example.com should actually still have, then we're requiring that certificate to actually be the current certificate. So basically from the very start of when the first certificate is issued, we are requiring a chain of trust through the old certificates going forward. So if we have a takeover situation, then whoever is taking over that specific domain should not have access to that certificate. But any legitimate owner should actually have that certificate, because they're usually updating it when it's close to expiration, hopefully. I mean, hopefully nobody's letting their certificates expire. But of course, there are cases where you might have a disaster recovery scenario where somebody might have lost the certificate because they might have thrown it away, the server died, for whatever reason. So in these cases, we can actually use stronger domain validation challenges, for example, that require more manual work. An example is the DNS-based challenges that you have already. There are cases with is-based challenges, which I guess with GDPR now is less of an option in the majority of cases. But overall, this basically means that we can actually identify these kind of takeover attacks fairly accurately. We can prevent TLS certificates to be issued then, which means we can downgrade takeover attacks that might be full impersonation attacks to at least down to denial of service attacks. At the same time, this doesn't really change anything for the end user. It increases some amount of work for the certificate authorities, but it also doesn't really have any drawbacks for the user, beyond the case of the disaster recovery that I mentioned, when you need to rebootstrap basically the chain of trust. Where do we go from here next? For us, we hope to actually have this coming out maybe as a ACMA validation challenge. So if anybody of the ACMA working group is here, we'd be happy to chat. We'll actually be attending the session, so hopefully we'll get a little bit more input there. And with that, I would like to thank you for your attention, and I'm happy to take any questions.
Yeah, Richard Barnes, author of the ACMA spec. So we're glad to have this. In fact, this was some stuff we considered in the early iteration. Back when looking for this sort of like hysteresis and prior validation. So this is a useful thing to bring back. I think we didn't do it in the first round because we're worried about some brittleness. But it seems like you've got some first help results with that. So yeah, I'm looking forward to having some proposals here.
Great, thank you.
Sorry,
So on that point, the brittleness that was pointed out by Richard, what are the use cases that you've thought out of a provider that has a certificate and is unable to hook it into the actual certificate validation thing? What challenges are there for someone to use a certificate, which is typically for TLS, in this case for a kind of a brand new protocol? What sort of challenges have you considered?
So, sorry, can you repeat the question?
Yeah, if you go back to the diagram.
This one? Is this one?
The one with the big loop, right? So if an old certificate was found, requested to be the current HTTPS certificate. In a lot of hosting provider scenarios, this is not something that you can just sort of send a certificate somewhere else for it to be the certificate used to prove the ACME challenge. What challenges do you see in making this practical? I mean, there's a reason that this was considered but not necessarily incorporated into ACME. What innovation is there here to make this easier for users to or service operators to use?
So in generally, I mean, I'm not sure if I'm understanding the question correctly, but so the way that the current ACME spec is that even if that challenge fails, you could basically go back to different challenge by offering multiple ones at the same time, and you only need one of them to succeed. So you could, for example, go with this one and then have the DNS-based validation challenge in there as well, which might actually require you to modify DNS records. So you have a nicer failover between the two. Does that answer your question a little bit?
A little bit. I'll leave it to the line.
I just on that point, John Nicholson. The DNS challenge is very easy to do. And why don't suggesting that first, or whenever you can, only do this when you absolutely need to do the web question?
You could also do that, just that in a majority of cases, at least from what I've seen, I'm not sure what, I'm sure Let's Encrypt has some statistics on what the defaults are, like what people opt to, which kind of challenges they are. But in a lot of cases, people are deploying this on their web server and they don't actually have necessarily immediate access to change the DNS. I mean, they can, it's just that for them, there's not direct API access, for example, or they don't want to deploy this immediately on the API. So this is, I guess, it's to some degree, it's a problem for small scale deployments rather than really large scale deployments where you have everything like automated in like a nice pipeline or continuous integration deployment setup.
So what I do at the moment, because I have a lot of machines that I don't want to open up to the web or web exchange, I want them to get a so a dedicated server to do begin tone and it hosts the certificates, and then the machines can complete and just for anyone's use, the documentation I have to do that is on dnsprivacy.org. That's only helping.
Thanks.
One last question. In the scenario of AWS, in what percentage of the case was CAA present and able to mitigate this?
Great question. So we haven't actually looked at how many of them had CAA records. The majority of that was also, so the data was collected before CAA records were mandatory to actually be checked. There's also the question, it doesn't really change the problem, right? Because just because it says, hey, only Let's Encrypt is allowed to issue a certificate, doesn't mean that the attacker cannot just go to Let's Encrypt and argue, right? Say it's like, hey, I would like to do the HTTP-based validation, because right now, at least, CAA records doesn't restrict which kind of challenges are there. There's currently on the Acme mailing list that's being discussed. There's some issues with which kinds of dashes and non-dashes you're allowed to have in there.
Okay, great. Let's thank the speaker. All right, our next speaker is Johanna Aman from ICSI/Corelight, and she is going to be talking about studying TLS usage in Android apps. We'll get this set up quickly. Great.
Thank you very much for the introduction. Thank you very much for the introduction. So I'm going to talk about studying the TLS usage in Android apps. And this is joint work with people at Stony Brook University, some more people at the International Computer Science Institute, Princeton, and the University of Massachusetts at Amherst. And the work here that I'm presenting here was mostly done by Abbas, who is sadly not able to attend the workshop today. So nowadays, as you know, encryption is basically everywhere. And especially after the Snowden releases in 2013, you have seen that more and more people know that the data should be protected when it's on the internet, and are aware of the privacy challenges that there are when data is not protected on the internet. And you can see that generally more and more web pages on the internet are encrypted. So in 2017, according to a lot of sources, we reached the point where more than 50% of the web is encrypted. And if you look at the quality of encryption, it has been increasing too. Google has been doing things like downgrading sites that don't use HTTPS and so on. But now the question is, how does all of this look like on mobile devices? Because on mobile devices, TLS also is important, but the ecosystem looks a little bit different. So on Android, about 88% of applications use TLS. But unlike on the desktop, where you basically have, most people are using the web browser to access the internet. And you have big groups of people who should hopefully know what they are doing. On Android, lots and lots of people use applications that then use TLS to communicate with the internet. And there are many opportunities to make mistakes when you implement TLS. And so what we aim to do in our work is that we wanted to understand how TLS is being used on Android. And typically, when you want to do something like this, you have two opportunities that you first look at, which is static analysis and dynamic analysis of the code that's running. Both of those aren't really that great in this circumstance, because static analysis, you never get a really full picture. With dynamic analysis, you first have to get the code paths that do TLS to actually execute, and you might not be able to do that. So what we did for this work is we use a software that is Lumen. And basically we crowdsource it. So we do user-space traffic monitoring on Android. We ask people to install the application, and the application then sends data back to us about the TLS handshake, and we look at the TLS handshake and what's happening. And the nice thing is that the data is also annotated a little bit with information like what application did this session come from. So you might think, wait a minute, we are actually getting TLS traffic from people who are running our app. And so our study has been cleared by UC Berkeley IRB and has been deemed non-human subject research. We anonymize the data. And the answer generally is that we are not interested in anything that the people are doing, or we are not interested in the users. We are just interested in the software. And when someone installs our application, you have to go through quite a few screens that make it clear what we are doing and what you are agreeing to. And you can obviously stop contributing your data at any point of time by just uninstalling the application again. And no, this just died. Here we are. Okay. Next thing, what exactly do we collect? We collect 3 key items. We collect the client hello, the server hello, including the certificate, and could I actually not have pictures? And we also include failures of our TLS proxy, which reveals certificate pinning. So in our study, this was first presented at ACM Connect last year. And in our study, we have data from 5,000 users in more than 500 countries, with more than 1.4 million connections, more than 7,000 applications, with more than 34,000 domains, and more than 800 unique device and OS combinations. And the data goes from the end of 2015 to mid-2017. So we do not have data in this talk about any later days. So what do we do with this data? So the first thing that we did is we do basically fingerprinting, because as it turns out, most TLS implementations out there, or if you set up a TLS connection, as you probably know, you advertise a ton of different cipher suites that you might support in a specific order. And it turns out that you can identify TLS implementations quite good just by looking at the cipher suites and the order in which the client sends it out. And so we made a list of the cipher suites that base Android installations send out OpenSSL, GNU TLS, NSS, and so on, and compared what applications are actually sending out. So what applications are using. And it turns out that 84% of the applications in our dataset actually just use the default SSL of Android with the default settings and don't change anything, which is a lot. But now the interesting question is, what does the rest do? And why do some of the applications on Android not use the default settings? And there are several answers. So in some cases, the answer is to improve security, because there are some people that have strong feelings about security and know exactly what they are doing. Like, for example, Facebook. They use OpenSSL, they remove weaker cipher suites, and they use the ALPN extension to negotiate, I think, a variant of HTTP2 that they are speaking. And you cannot do any of that with the default implementation of SSL on Android. Twitter uses the default implementation and removes a few weaker libraries. But naturally, then you have some people that do it wrong. Like, we have some private messaging apps and VoIP apps that use a really short cipher suite list that does not include any forward secure ciphers for some reason. And then there's other software that does uses their own libraries for different reasons. Like, for example, Firefox uses NSS, which is their own cryptographic library, which they use on all operating systems where they can, and NSS is generally really good, so that's okay. And VLC and SoundCloud use GNU TLS, at least in some versions, which also they just might do everywhere. So another thing that we looked at is, when do we see, or do we see people using weak and outdated primitives? And here a few interesting things come in. For example, SSL version 3 is still supported by anyone running any app running on Android 5 or below that uses the standard operating system library. And at the time that we wrote this paper, Android 5 was still running on more than 61% of phones. I looked yesterday evening, and Android 5.0 and below is still used in more than 20% of devices that currently connect to the Google Play Store. So this is a significant amount of devices. And on Android, as you're probably aware, you don't actually get updates all that often. So once you buy your phone, you even if Google brings out a new operating system version and it's available for that phone, you might not get it because your operator also has to make it available for you. And for older phones, it's kind of unlikely that the operating system will even be available for your phone. Then there are other applications like some EA game apps. When we did our measurement, enabled SSL version 3 on all versions of Android. We had some application that allowed null or anonymous ciphers that had, once again, hundreds of millions of installs, where you can potentially just do a man-in-the-middle attack, where you put yourself into the middle, and your server says, I speak this anonymous cipher, and you let them connect to you. And if they actually don't enforce that a certificate is present later during the verification, which we did not test, you have a man-in-the-middle attack. Then export-grade ciphers, which should not be used anymore at all and can generally be man-in-the-middle, are still used in Android, are available by default on Android 4 and below, which is used on still, yesterday it was more than 10% of devices and some big apps again. And generally what we observe is that most apps with weak cipher suites use poorly configured OpenSSL. So they are doing things themselves, obviously. So, solutions. What can we do about this? So in our opinion, one good thing that Google could do is to basically decouple TLS updates from operating system updates, because as I noted, the big majority of applications just uses the operating system default installation, and when the operating system default installation becomes outdated, like with Android 5, and still tons of people use it, you speak outdated primitives of TLS. So that would be one nice solution. They actually already kind of do that for their own services. So Google Play Services bundles its own TLS library and is updated independently of the operating system. And in general, it also would be nice to give more options to the developers, because some developers apparently opt to use OpenSSL instead of the operating system version to be able to set TLS extensions, but you currently cannot do with the operating system TLS implementation. Then another thing that we looked at, and that kind of builds on earlier work, is that Android root stores often have impurities. So you set your telephone ships with a root store, and we have shown in some of our earlier work that often vendors insert root certificates into that root store. Like if you have a phone from that's built by LG or another company, they might insert a root certificate into your root store because they are using it. And some apps also on Android, and again, don't use the root store of the phone, but just ship their own root store instead. Or pin server certificates, or use self-signed certificate. For example, Firefox has its own CA store, Uber, Google, and PayPal, and Facebook use certificate pinning, and so on. And that is all good and can be really great for security, actually, but you also can make interesting mistakes when using something like this. So when we look at how things are being used, is that most applications just trust the operating system provided trust store. That means that any CA that's in there is trusted, including any CAs that your phone vendor might insert into it, which you might not actually want to trust. And then some apps pin certificates to mitigate certain attacks. which is really great. But we also found one app that did it really poorly. So was one major system recovery app with root access and so on that downloaded its root store over HTTP. So over HTTP in the clear. So if you intercepted that and gave it your root store, then it would trust that. So the question once again is, how can we fix this? And what do we do with the polluted CA certificate stores that a lot of Android devices actually have? And in our opinion, this is once again just something that Google can do for Android, because they can or should be able to ensure via some agreements that you cannot just insert your own root certificates when you sell a phone. And what's also interesting is that it probably shouldn't even be necessary, because even if like your phone vendor has its own CA that it needs for its apps, it should be able to just use that in its own apps and not just insert it in the operating system root store so that everyone trusts it. So perhaps they could make primitives available to make that easier. And another thing they could do about people using their own libraries is they should at least make sure that people are properly educated about what they are doing, and potentially do some basic checking that people use OpenSSL, for example, correctly, or that they have that a basic connection that's made by the app is at least reasonably secure. They kind of have done something like this in the past. So there was an security issue with GNU-TLS, where they prevented you from uploading applications that bundled a vulnerable version of GNU-TLS to the App Store, and you got a notification that basically told you how you can fix this. So, in summary, we made the first study of TLS usage on Android apps at scale. The majority of apps just uses what the operating system provides by default, and applications are often potentially vulnerable to attacks when the operating systems get outdated, which happens a lot. If you use third-party libraries, a lot of people make mistakes during the configuration. We found a little bit of people doing certificate pinning for security, and we have shown a few potential solutions. And now, if you have any questions, I would be happy to answer them.
Hi, Leif Johansson. This is not a question, it's a pointer to prior work. There is a couple of guys from Kirei, Jakob Schlüter, and some people who are known in the DNSSEC community did a tool on GitHub called CAT, C-A-T-T, which was set up to build and track client CA stores over time. It might be worth taking a look at. It's on GitHub.
And for online, apparently the microphone is not going through. Just this was a note that there is a tool called CAT, C-A-T-T, for tracking client root stores.
Just wondering why you did the study with real users and having them install your certs on their phones. It seems like you could have just done this study in the lab. Just download all the apps to a phone that you control, and then do all the studies without compromising the privacy of however many users you exploited here.
Let me repeat that for online. So the question was, why was this done with real users rather than in the lab?
So the answer is twofold. So first, I don't think we exploit users because we make them really aware what they are doing.
I'm sure they read all 5 of those screens very carefully.
And on the second note, it's not actually, so you cannot often not just install an app and start it and hope that it makes a TLS connection, because a lot of the applications need user interactions to make all of their connections. And I know that there are some things that you can do with trying to...
You could do that in the lab? You couldn't open the app in the lab?
With 20,000 apps?
I mean, there are automation tools.
There are automation tools, but then again, you have
can be done.
Then you have the problem that the automation tools typically aren't all that great at getting into the right code path, because once there's a sign-up screen, what do you do? So the ones that I know basically tap around the screen more or less randomly and hope that something happens. And this actually shows you what is being used in practice. So,
do you have the user delete your CA when you completed the study? Did the users delete your cert when they completed the study?
It doesn't matter, is the interesting thing, because it's generated onto the phone. So and the private key is destroyed. So it's an unusable certificate afterwards.
So part of the point of this app is not just to do this study, but it's a more general tool to sort of study, people's habits and behaviors of things on phones. So some of that stuff we can't do in the lab, but sort of since we have this tool, Johanna and her team here have been able to do this particular study. I mean, I think that's another answer.
Brett Jordan, thanks for doing the research. Stuff like this is very valuable. It helps enlighten all the work that gets done here at the IETF. So regardless of the means and concerns, you very clearly told people what you were doing. So thank you for doing the research.
Thank you.
If there are no more questions, well, thank you, Johanna.
Thank you.
All right, there will be a short 10-minute break, and then we'll resume with the next session.
We'll be back at 10:10. Okay, 15 minutes. Thanks.
Could I test real quick just so it works for the thing?
Except that the HDMI.
I think the mic issue is resolved according to.
Hi, sure. How are you? Which mic have you got? Yeah, I saw the picture. It's a she, right?
Yeah, Lila. But I'm so excited because that I was very
Oh,
yeah.
Organizing.
So
should I?
I hope it comes to staying.
Yeah.
Comments on the
So I should be able to use my laptop. Hey there, how's it going? Good.
Even
Wow.
if it was like genius, if not also standard, it's not very helpful.
Yeah, I'm gonna go.
Let me try. So you're after me?
Yes.
Congratulations.
Yep. Right.